Can you see the screen again? I start recording. Can anyone confirm me
Yes,
that
sir.
you can hear me and you can see the slides? Right? So this is what we are talking about. So you have the roof, and on the roof you have tiles or the sheet, and because of the weight of the tiles or the sheet, the structural members, which are wooden timber parts, are going to be loaded externally. What my question was that when you have an external load, do the structural components generate internal forces? If so, what is the reason? There are only three of you. Please talk. If not, it will be only me talking in front of a screen. So what is the reason for this? If there are internal forces, how they generate it? And what's the reason? But why it is leading to internal forces? Now you need to understand that when you have a structural component externally loaded, right, that whole component must be in equilibrium. Can you see this slide? You have a column or beam which is represented by A and B. And there are two forces, F and minus F, equal and opposite. So this beam or the rod is in equilibrium, right? You have F on this side and F on the other side. So it is in equilibrium. Now what you need to understand is that if you make a cut across a point like C, right, still the two parts which is represented by AC and CB is in equilibrium. Is it true? No matter wherever you make imaginary cross cut in a loaded beam or a column, still that part is in equilibrium, right? Otherwise, it will start to accelerate. So we know that it is, if that is the case, then when you load the beam immediately, it will try to move away. That doesn't happen. That means even you have make an imaginary cut at point C, still these two parts must be in equilibrium, right? Now the problem is how that internal force is generated. And not only that, right? You know, when you move a force, now this case is an axially load case. So the things are much easy, but when you have a load like this, right? There are two loads on a simply supported beam. In such a case, you will see that when you make a cut at an arbitrary place, you need to have not only a force for the equilibrium of that particular part, you also will need a moment, right? Because if you take this part AB and I'm going to make a cut somewhere before the B, then you have a reaction here. And again, to stop that reaction at A, you need to have an opposite force with the same size. Then what happens is that you have equal and opposite forces, and there's a distance between them which will make the system to rotate, right? But if this whole thing is under equilibrium, you know that it cannot rotate. That means the beam not only have to generate a counter force, but also it need to generate a counter moment. So that is how whatever the structural component, maybe a column, maybe a beam, maybe a part in a machine, whatever it is, when it is under an external load, that structural component must generate a force and a moment, right? So any questions up to here? No? Okay. Now let's see how we can compute this force and the moment. The first part of the slides are how to calculate the external forces, and when you make a cut at some point, how to calculate the internal forces. So let's try one of them. So this is the problem, right? We will do a simple one. Let's try this one. You have beam AD and two forces P1 and P2. Suppose that we are going to make a cut in between A and B, and you need to compute what are the forces acting on that particular part. Can you do it or try it quickly? Make a cross section out somewhere here between A and B. Now, can you see my paper?
Yes, sir.
Okay. So let's try to do this question very quickly. We have two forces, P1, P2, right? So this is A, B, C, and D. Let's suppose the distances are, let's take, here it is x1, and this one, let's stay up to here, it is x2, and up to here it is x3, right? We don't need all of these things because for this exercise, what we're going to do is to make a cross section somewhere here, right? When you get such a question, what is the first thing to do? What the first you are going to calculate? You can't do the first step, then that means you cannot progress after that. You got such a question for the exam, right? So what is the first thing to do? You need to compute all the external forces. So in this case, this is a simply supported one. So at this point, let's take first the point D here. This is the roller support. What do you mean by roller support? It can generate only a one reaction which is perpendicular to the common point between the knife edge and this beam. So only this direction. It can generate only vertical force. Let's say R at D. There's nothing else. This one can generate or it can restrict motion in two directions, but since this is only upward, that means this must also be only upward, right? So that is the external reactions. Now we can draw the free body diagram for this question. This is the beam A and D. At A, we have one reaction RA. At D, we have another reaction RD. And in between, we have P1 force and P2 force, right? Then what we need to do is find RA and RD. So do that quickly. You know what to do. We can apply vertical force balance. So RA plus RB is equal to P1 plus P2, right? Then what we can do? We can take moment around one point. Let's say it is A. We have RB into X3 minus E1 into X1 minus E2 into X2, right? Now we have two unknowns and two equations, so you can find RA and RD. So let's do a little bit of simplification. RD is E1 X1 P2 X2 or X3. Then that means RA is X3 E1 plus E2 minus right? So don't worry about the values, because when there is actual question, you will have the lengths and the forces. Here what we need to know is that we can solve these two reactions, RA and RD. So we know what they are. Then we are going to make a cut at here. Let's suppose the distance from A to this point is X, right? So I'm going to know that part. Here is the reaction RA, and this is in equilibrium. That means we need another force which is acting downward. Typically we note it as V, Vx, and we have two opposite forces. That means we need the moment to stop this piece rotating. That one is M at X. Any questions?
No, sir.
Fine, right? And the distance from this point is X. Now you can find Vx and Mx. So do it quickly. So when you apply the force balance, you will see that this Vx is equal to Ra, and this Mx is how much? You can take moment around this.
Vx multiplication X.
How much?
Vx multiplication X.
Yeah, typically, but we take it from this point because Ra is the known quantity, right?
Okay.
So Ra into X. That also correct what you told, but take it at this point, which is the unknown. Right? So this is the process to calculate the internal forces or moments acting on a beam, column, or any other structural component, right? But remember, as you can see from this equation, for the moment is going to depend on what? Is it a constant?
No, sir.
It is not a constant, right? Because this mx have a distant part. That means the bending moment is going to change depending on the point which you are going to consider on the structural component, right? So in this case, when the distance increases, your bending moment or the moment is also going to increase, right? This is obvious, right? When you have a long beam and when you push it at the mid, you will see it will try to slack. That happens because of this moment. Exactly, nothing else, right? So in this case, the shear force is a constant in between these 2 points, but that is not the case for all the loading systems. So let's see what will happen if we have slightly different loading system. Before going to loading, we will consider what are the possible supports that you can have on a structural component, right? When it comes to structural analysis, we have 2 different types of systems. One is statically determinant and the other one is statically indeterminate. So what's the difference between these two? How we say something is statically determinant? මොකක්ද මේ දෙන්නගේ වෙනස? Statically determinant system එකයි statically indeterminate system එක. No idea? What's the difference between statically determinant and statically indeterminate? We call something statically determinant if we have enough equations to solve the problem completely, right? With using only the equilibrium conditions, we can solve the system completely. Like in this one, which we done for the previous case, you have a beam on one side on a knife edge and other one on a roller support. So this one you can solve completely as we did in the previous case. Same thing with here, even though the beam is overhang, you have only 2 upward reactions and it can be completely solved. Or cantilevered beam, right? We know that at the support, there will be a reaction and a moment, which can be completely computed with applying the equilibrium equations. But when it comes to a beam like this, where you have one knife edge and two roller supports, you will see that there will be three unknowns and you can get only two equations by applying the equilibrium condition, right? So this one will not be able to solve completely using the equilibrium condition. Same thing in here. You have a cantilevered beam, but it is supported at the end. Right? In this case also, you will see that there are more unknowns than the equations coming from the equilibrium condition. Same thing with this one. The beam is fixed on both ends, and again, we cannot solve this problem completely with only the equilibrium equations. So any questions about determinant and indeterminate beams?
No, sir.
Okay. Can you understand what it means?
Yes, sir.
That is about supports. So how we can compute when it is statically indeterminate? Right? These things are there in our day-to-day practice. We will find these kind of supports. If you come across such a thing, what to do? Even this one, a fixed beam between two fixed supports. You need other conditions, either from the geometry or the constitutional equations, right? Like Young's equation, something like that. We need extra equations if we come across such a systems. Some may be from geometry, right? And some may be from other material constraints. And when it comes to loads, we come across mainly two different types. One is the point load, as what we used in the previous example. You have 2 points load. Why we call them as point load? Because they act only at the point, like this P2 and P3, right? They act at a point on the beam. But some loads are there, they act just like a pressure all along the length, such this W1 in here, right? So as an example, we can consider something like a roofing sheet weight acting on a rafter, right? It is a distributed load, or the weight of the slab acting on a slab beam, right? The beam supporting a concrete slab is loaded in this way, right? Distributed load. It is not a point load, right? And when it comes to distributed load, they can come with various different distributions. Some will be equally distributed throughout the beam. You have the same value. Or sometimes they may have different shapes. Sometimes it will go up and come down like triangle. Or they may have quadratic variation with the length, right? Any different types of loads can come when it comes to distributed load. Now, if you have such a distributed load, how to find the resultant of such a system? Right, point load, yes, we know where it acts and we know how large it is, so we can get the equilibrium very easily. But if you have a distributed load, what to do? How to find the resultant due to the distributed load? මහිම මොකද කරන්නේ?
සර් මේ අර අර ඒකාකාරවම තියෙනවා නම් හැමතිස්සෙම හැමතැනටම බලේ එතකොට වේට් එකකින් ඒකේ තියෙන දුරත් එක්ක මල්ටිප්ලයි කරලා ගන්න පුළුවන්.
ඔව් පොතෙන් දැක් කරන්නේ. ඒකාකාරව තියෙනවා නම් වැඩි ලේසි. මොකක්ද අපි ගන්න තියරි එකකට? ටෝටල් එක කොච්චරද වෙන්නේ? ඒකාකාර නෙමෙයි නම් ට්‍රයැන්ගල් එකක් හරි එහෙම නැත්නම් ලීනියරි ඉන්ක්‍රීසිං ලෝඩ් එකක් හරි නැත්නම් quadratic එකක් නම්
no ideas.
So the force is area under this curve. So if you have a constant distributed load, then W1 into height is the total force. If it is anything else, like a triangle, still you can compute the area. If it is a quadratic or cubic relation, you may need to integrate. But whatever it is, the total force or the resultant magnitude is the area under the curve. That's fine. Then where it acts, the point of action of the resultant, මේවාගේ distribute equal distributed නම් මොකක්ද?
center ඒ force එකේ තියෙන center.
මේකේ center point එක. Same thing with any other shape, you have to compute the centroid point to find the point of action of the resultant. I hope you know how to compute centroid, right? Section before this is about centroid of areas, remember?
Yes.
So you need to compute two things if it is a complex distributed load. One is the area under the load, which will give you the resultant magnitude. And the other one is the centroid point of that distributed load, which will give you the point of action, right? Okay, let's do a very simple question and try to draw or try to compute the bending moment and the shear force. Right? One of the most simplest case comes under this is the simply supported beam with one point load at the mid of the beam, like this one. Right? There is the beam AB. It is simply supported. One side is a knife edge and the other one is a roller support. And the load is acting at the center point. As you can see, this is L/2 and this is L/2. Now your task is to find the shear force and the bending moment throughout the beam. So can you start? First is to find the external forces, then draw the free body diagram, or even before that you can draw the diagram and find the external forces, and then you have to make sections at each important points. In here we know that we have one distribution from A to D up to this external point load, and then another part from D to B. So we are going to make cut between A to D and another cut between D to B. So in here it is represented as C and E. So first draw the feeble diagram and compute the external forces at A and B. How much is the reactions at A and B?
P over 2.
P over
2.
2, and they are equal, right? Because the system
Yeah.
is symmetric. So you get P over 2 on both sides, right? Now make the cross sections at point C. Here, point C is in between A and D. And consider the part A to C. You can see my screen, right?
Yes, sir.
So I'm not going to do the whole thing. I'm going to do the part AC. We have a reaction here, which is P over 2. And this point is A, this point is C. To stop this force, we need a downward force at here, which will be Vx. And there is a moment which tried to rotate this or tipple this like this. So we need a counter moment in here, which is the bending moment actually Mx. Right? Now compute Vx and Mx. Vx is directly how much? P over 2, right? And Mx is how much?
P over 2 multiplication X.
P over 2 times X, right? Now this two equations valid only from A to until point D, right? You can't go beyond that because the conditions are going to change after point D. Okay. So we have to make another cut after point D. So let's do that cut. A, and at point D we have load P, and this is point D. This is point D. Here we have the reaction P over 2, and the total length from here again we are measuring from A will be X. Now again, do the same thing we did for the previous case. Right? There are two forces. One is upward, one is downward, but typically we mark this as downward force, Vx. If it is upward, you will get a minus sign. Right? And then we have, just like in the previous case, a moment acting here. Now compute Vx and Mx. What are the values? This load P is at the exact halfway, that means L over 2.
3p over 2 Vx 3p over 2 mx p over 2 multiplication x plus p multiplication x minus L over 2.
How much the Vx?
3p over 2.
How you got that value? So let's apply
P plus
downward direction. Vx minus p over 2 plus p equals 0, right?
minus. Okay.
Then Vx is how much? Minus p over
P
2.
over
Bending moment? Again the same thing.
Minus p.
This point and apply the moment.
Minus p over 2 x plus p multiplication x minus L over 2.
It is not that complicated. Let's see. So let's consider moment at this point. Mx, you have this p, which is in the same direction. So plus p into x minus L over 2. Then this one is in the opposite direction, minus p over 2 into x, right? Is this what you got as the equation?
Mx is equal to p over 2x plus p over 2x minus p multiplication x minus L over 2.
And next, this will simplify. This is dx
3p
2 again. Is plus, so it will be
minus p
p times x minus L over 2. So 0 when it goes to other side, mx is p over 2 L minus x. Correct?
yes sir.
Okay. Now we have the variation from point A to point D as well as point D to point B. Right? So typically, since the shear force and the bending moment varies with the length, we give them as two diagrams, shear force diagram and bending moment diagram, and we show the variation throughout the beam. Let's suppose this is the total length L, right? And this may be the midpoint L over 2. This is the variation of shear force Bx, right? From what we found up to point D, how much is shear force? It is P over 2. So up to here it is a constant value with P over 2, right? And after this point load at point D, it suddenly becomes minus P over 2. So from here, it will go to the minus potential and will be same until it ends. And this one is minus P over 2. Correct?
Yes.
Now, when you look at this is the most important thing. You need to understand that this shear force diagram shows all of your point loads. Can you see? At the beginning, at point A, we have a point load at A, which is the reaction. The value is P over 2. So this is that height, right? And when it comes to point D, you can see that there's a downward force with value P, and exactly this distance is how much? From this point to this point, it is P. So remember, when you draw the shear force diagram, all the point loads must be